Okay, thank you very much. I'm really happy to be back here. Like Margot said, I was a circus fellow for 2 years, but I haven't been back for 4 years, so it's really a pleasure to be back at Harvard and part of this really interesting symposium. What I want to tell you about today is about fair division. This talk was actually prepared in advance. I'm happy that a lot of people mentioned fairness. I'm going to take a specific perspective on fairness. As part of this theory that has been around since the 1940s, it's a topic that's been studied by economists, mathematicians, political scientists. I'm going to take a more computer science perspective. Computer scientists have been involved mainly in the last decade or so. And there are many algorithmic and computational challenges in fair division. Another thing we're interested in is the implementation aspect and making these methods accessible to people. So those are the kind of things I'll be talking about. But I want to first start with a remark that's sort of important to me to make as somebody who also thinks about game theory and incentives. And I'll make this remark through the story of this guy, Jean-Charles de Borda, the Chevalier de Borda. So he was an 18th century French mathematician and engineer and a member of the French Academy of Sciences. And one of the contributions he's known for is for introducing a voting rule called Borda count, which was actually used in the French Academy of Sciences. Now, when he introduced the rule and proposed it, he was approached by other people in the academy, and they told him, Monsieur Borda, your rule is highly manipulable in the sense that it's really compelling for people to lie about their preferences in order to get a better outcome in the election. And Borda's immortal response was, my rule is intended for honest men. Now, one anecdote I want to make here is that, I would like to tell you that the guy in the picture is actually Borda, but there are no good pictures of Borda online. So finally, in desperation, I ended up Googling for random 18th century French dude, and this guy showed up. I have no idea who this guy is. But really, the point I want to make here, is that for the purposes of this talk, my rules are intended for honest people, in the sense that I'm going to put aside game theoretic considerations and really focus on fairness issues, try to distill what fairness means and how to achieve it. Okay, so to talk about fair division, I want to start from another true story. This happened in 2001 when I was starting my undergraduate degree at the Hebrew University of Jerusalem. And the plan was to share an apartment with 2 friends from the army, Nir Ben Moshe, who's actually got a job this year as a philosophy professor at the University of Illinois, and Nomi Sender, another friend of ours. And as things turned out, when we had to look for the apartment, Nir was on this long trip in South America having fun, and Nomi and I searched for the apartment alone. We found a really nice one with 3 bedrooms in a great place. When Nir came back, he liked the apartment. Oh, one thing to know about this apartment is that it had 2 identical rooms, but then the third one was clearly much better. So it was, this larger room, like a corner room with 2 windows and a nice view. And when Nir came back, he was happy with the apartment, but his position was, because I didn't participate in searching for the apartment, I should get the best room for the same price that you guys are paying, which somehow made sense at the time. It's hard to argue with philosophers, but in retrospect, it's not a very fair solution. So what I want to think about for a few minutes is what would be a fair solution in the context of rent division. So let's look at this example with 3 bedrooms and a total rent of $10. And I will have 3 players, green, blue, and red. The assumption we'll make is that for each player, his value for the 3 rooms add up to the total rent. So for room 1, the values are $6 for green, $5 for blue, and $4 for red. These are the values for room 2. And for room 3, everybody values at $2. Now next, I'm going to take the total rent and divide it between the rooms by setting a price for each room. And the way to think about these prices is if my value for a room is X and I get it for price Y, my utility will be X minus Y. Okay? So room 1 will have a price of 5, and then the utility of the green player will be 1, 6 value minus 5 price. The utility of the blue player would be 0 if he got that room, and the utility of the red player, if he got that room for that price, would be minus 1. So we'll set a price of 3 for room 2 and a price of 2 for room 3. Next, I'm going to assign the rooms. So I'll give room 1 to the green player, room 2 to the red player, and room 3 to the blue player. Now, what I want to claim is that this solution, this allocation of the rooms and division of the rent, satisfies a really compelling fairness property called envy-freeness. What this means is that the value of each player, the utility of each player for his room at his price, is at least as high as his utility for any other room for the price of that room. So for example, if you look at the green player, he has utility 1 for his room, utility -1 for room 2 for the price of 3, and utility 0 for room 3. The red player has utility 1 for his room, -1 for room 1, and 0 for room 3. The blue player has utility 0 for his room, but he also has utility 0 for the 2 other rooms for the prices of those rooms. So nobody is envious of the allocation and price that any other player got. And this, I think, is something really beautiful, that you can take something that seems as abstract as envy and really capture it in such a concise and rigorous way. And this is really one source of the beauty and power of fair division theory. Now, what makes envy-freeness really powerful here is, it's not only something you can have in this example, but it's something that under the assumptions we made is always possible to guarantee. So in any situation, we'll always have an envy-free solution. And even better, from the computer science point of view, you can find an envy-free solution in polynomial time, in a computationally efficient way. So it's this really compelling solution, and you can compute it relatively easily. Now, the thing is that envy-freeness in and of itself is not sufficient in order to get intuitive outcomes in every situation. So let me give you an example. It's similar to the one we had before, but let's say the total rent will only be $3 now. And the players will have the following weird values. Player 1 only likes room 1, the green guy. The red player only likes room 2. And the blue player only likes room 3. And I'll set the prices in the following weird way. I'll put the entire rent on room 1. Okay, so it costs $3. The other 2 rooms are free. And finally, I'll assign the rooms in the same way that we had before, with room 1 going to green, room 2 to red, and room 3 to blue. Now, this allocation, this solution is also envy-free, because the blue player and the red player are obviously happy. What about the green player? He has utility 0 for his room for the price of 3, but he also has utility 0 for getting the other rooms for free because he has no value for these other rooms. So this is envy-free, but this is not the intuitive solution here, right? So the intuitive thing to do here would be to assign the rooms in the same way, but equally divide the rent between the 3 players so that each player pays $1. Now, one way to get the solution in this example is to say, I want envy-freeness, but subject to envy-freeness, I'll add an optimization objective, which will be maximize the minimum utility of any player. Okay, if you have an objective like that, that would give you this solution on this example. And in general, it gives really intuitive solutions on many examples that you can think of. So one piece of good news, and this is from ongoing work with Kobi Gal, Moshik Mash, and Yair Zik, is that even if you add this optimization objective on top of envy-freeness, you can still find an optimal envy-free solution in polynomial time in a computationally efficient way. Okay, so this underlies a deployed algorithm for rent division that I'll mention later, and it in general gives a really nice way to approach the rent division problem. However, envy-freeness is not something that we can rely on in every situation where we think about fair division. So I want to give you an example of a different paradigmatic setting of indivisible goods and try to think about fairness here. So indivisible goods can be things like precious stones or jewelry or artwork. And the assumption we'll make is that the players have additive valuations in the sense that if I give you the diamond and the statue, your value for getting both is the sum of values. Now, here, obviously, envy-freeness is not something we can guarantee, because if you have 2 players and both of them really desire the diamond and don't really care for the statue, I have to give the diamond to one of them if I want to allocate all of the goods, but then the other player would be envious. Right? I can't break the goods between the players. So envy-freeness is not something that I can guarantee here. And what I want to think about is what kind of fairness notion can we always guarantee in the face of indivisibilities. So the approach will come from this idea of maximum share guarantee, which I want to introduce through this estate division example. So let's say that we have this estate, and it has a house and some artwork and some cars and some jewelry, and I want to divide it between 3 sisters. So what I'll do is I'll go to the eldest sister, and I'll tell her, look, I give you the privilege of dividing the items into 3 bundles. So you get to choose the bundles, but then your sisters will get to choose before you. So this eldest sister looks at the items, and she's like, well, I like the house. That's where I grew up in, so let's say $30. The Mona Lisa is obviously very valuable, so $50. This other painting is actually a Jackson Pollock painting, but it looks like garbage, so maybe $2. And she doesn't really care about the other stuff, so these are the values. So one thing she can do is divide the items into bundles in this way, where she puts the house and the Mona Lisa in singleton bundles and the rest of the junk in a third bundle. In this way, her minimum value for any bundle is $20. So she can guarantee to herself a value of $20 no matter what her sisters do. Okay, so then the sisters start choosing. So maybe the middle sister chooses the large bundle, and the youngest sister chooses the Mona Lisa. And the divider, the eldest sister, is left with the house, which is a pretty good outcome. But now the youngest sister, the one who chose second, can say, look, I'm not really happy with this outcome, because here are my values for the items. So I really want the ring, I want to rule the world, and I like the 2 cars, but I don't really care for the other stuff. So if you gave me the privilege of dividing the items into bundles, I would put the ring in one bundle and the 2 cars in 2 different bundles. And this way I can guarantee to myself a value of $30 no matter what happens, which I wasn't getting before. Before I was only getting $10. So she says, this is not fair. I'm not happy with not having the privilege of dividing the items. So the question is, can we divide the items in a centralized way, in a way that simultaneously every player receives at least as much value as what they could guarantee if they were the one to divide the items but chose less? So this is this concept called maximum share guarantee. It was introduced by Eric Budish, who's actually a Harvard graduate now at the University of Chicago, in 2011. And the maximum share guarantee of a player is defined to be his value for the worst bundle under the best partition into bundles from the point of view of that player. So this in general is something that can be different for every player. Now for a few years, people believed that under additive valuations, it should be possible to always guarantee each player at least his maximum share guarantee. In fact, several groups have run very extensive computational experiments that haven't yielded a single counterexample. So one piece of bad news comes from a paper with my student Junxing Wang in 2014. So what we show is that if you have at least 3 players, there will always be examples where you cannot give each player his maximum share guarantee. There is no maximum share allocations, even under additive valuations. So, the examples are very intricate, so it's not something that you would expect to happen in practice. But this says we can't rely on maximum share as a hard fairness guarantee that we can say, we can give this to you no matter what. The good news comes from taking a computational thinking viewpoint, adopting an approach that's common in computer science, and asking, is there some value alpha such that we can always guarantee each player an alpha fraction of their maximum share guarantee? And it turns out that the answer is yes, with alpha equals 2/3. So we show that it's always possible to guarantee each player 2/3 of his maximum share guarantee. Now, this is a result that I really like on a theoretical level, so I think the proof is quite interesting. But one reason I'm really excited about it is that it underlies an algorithm for dividing goods on a website called Splitit. So I want to take a few minutes to tell you about Splitit. Okay, so Splitit is a fair division website. It's not for profit, and this is really important to me. The initial idea behind Splitit is that there's this vast literature on fair division, including many useful solutions for everyday problems, but most of them have never been implemented. So one idea was, let's take some methods developed in my group, but also by many other people over the years, and just make them accessible to people. A second goal is outreach. So just telling people about the beauty of math and economics and computer science through this topic of fair division that people can pretty easily relate to. Now the slogan of Splitit is provably fair solutions. And really the idea is that in each one of the applications, we want to give guarantees that are guarantees, that we can say we can always give this to you no matter what. Currently, there are 5 applications for dividing rent, fare, credit, goods, and tasks. For n division, what we do is basically what I told you before. So subject to envy-freeness, we maximize the minimum value of any player in polynomial time. So I haven't told you about the implementation details, but this is really the important part. I want to spend 2 minutes telling you about the application for dividing goods and how it relates to the theorems we just talked about. So for dividing goods, what we do is we look at 3 levels of fairness. The highest is envy-freeness. The middle one is called proportionality, which means each of the n players receives at least 1 over n of his value for getting all of the goods. And the lowest level is maximum share guarantee. And then we find the highest feasible level of fairness, and subject to that, maximize social welfare, which is the sum of values people have for their bundles. Now, if we had to go all the way down to maximum share guarantee, we maximize the alpha such that everyone gets at least an alpha fraction of their maximum share guarantee. In practice, this alpha will always be 1, because it's almost impossible to find examples where you can't guarantee everybody their full maximum share guarantee. But what the theorem allows us to do is give a hard fairness guarantee. So let's see how this plays a role. If you go to the page for the dividing goods algorithm, there's a description of the fairness properties. So we talk about maximum share and what it is. We actually have a nice animation on the website for illustrating it. But then we say, if you look at this highlighted paragraph, we guarantee each participant at least 2/3 of our maximum share guarantee. So this is the hard fairness guarantee that the theorem allows us to give. In practice, it's extremely likely that each participant will receive her full maximum share guarantee. Okay, but what the theorem lets us do is write this thing, which is the provably fair solution, the hard fairness guarantee that we can give. So, as you can probably see, I'm pretty excited about SplitIt. I think it's been a lot of fun. We've had more than 50,000 users so far, and a lot of really positive feedback, so I think it's really helping people. One point I wanted to make is Ben Adida mentioned this thing of you put your code on GitHub, and then people steal your AWS credentials and use it for Bitcoin. That happened to us. So we did put the code on GitHub at some point. 2 hours later, we lost like thousands of dollars. But the good news, if you want to be positive about this, is Amazon were the one that detected it a few hours later. They got in touch, we fixed the problem, and they gave us the money back. So, it does happen, but Amazon were extremely great about taking care of it. They did, yeah. Yeah, I mean, it was really impressive. Okay, so what I want to tell you in the last few minutes is another implication of SplitIt that's maybe a bit less obvious. So one thing that's happening is that as people are hearing about fair division, they're coming up with new problems that fit this framework, or maybe adjusting their old problems to fit this way of thinking. And this was actually foreseen by Hervé Moulin, who's an esteemed economist and now also an official advisor to SplitIt, but he's been a huge help over the years in thinking about SplitIt. And this is something that he sent to me by email in 2013. So he said, the reward of helping people who have a real fair division problem by explaining our solutions is that they in return pose interesting and difficult new questions, food for our thoughts. It could be a goldmine of ideas as well as a costly proposition if there are too many questions. And this statement turned out to be prophetic in a sense because we did receive many interesting and difficult new questions. And what I want to tell you in the last 2 minutes is about the question that was maybe the most interesting and the most difficult. So this is a screenshot of an email that was sent to me by a representative of one of the large California school districts in May last year. And what he says is, I heard about SplitIt, and I was intrigued because school districts are tasked with a similar, albeit more complex problem every year in the form of Proposition 39 requests. I'll tell you what that is in a minute. California school districts are required to provide any unused space to charter schools who apply. Oftentimes, there are more applicants than space available, and the result is the allocation of space becomes a political process that ends in an inefficient use of space and resources. And of course, what he wants is to use fair division theory to come up with a better solution. Now, what's Proposition 39? It's a California law that deals with many things. One of them is education. And here's what the law says. This is a quote from the law in the context of this problem of allocating space to charter schools. So it says, public school facilities should be shared fairly among all public school pupils, including those in charter schools. But of course, the issue is that the law doesn't define what fairly means, and charter schools and school districts have very different views on what fairness means here. And this has actually given rise to lawsuits brought by charter schools and the California Charter School Association against school districts, basically saying you didn't do things in a fair way. So the goal here is, of course, to come up with a provably fair solution that makes people happy. From the legal viewpoint, and there are legal scholars here who probably have a much better perspective, but from the legal viewpoint, whether provable fairness is an argument that can hold in a court of law remains to be seen. So the situation right now is that we have a method that we're very proud of. It has great theoretical properties. This is, by the way, work with my students Nisarg Shah and Dave Kurokawa. It has great theoretical properties. It has some really nice results on real data. And it has some really nice implementation details. It's a non-trivial implementation to get it to scale. Right now, our focus is on a collaboration with the LA Unified School District, which is the largest in California and the second largest in the nation. And of course, the goal here is to deploy the method or a variant thereof in the near future. So that's all I had for today. Thank you very much.
Time for a couple questions. Yes, Scott.
I'm Scott Commoner, as a current service associate and junior fellow at the Society of Fellows. Awesome talk.
Okay.
Really cool part because I work with all types. I wonder if you could tell us something about the insight that led to the counterexamples for the maximum share guarantee. I know this was like a very hard problem.
Yeah. So that's a very interesting question that's hard to give a concise answer to. Let me try to say briefly. So the way the counterexample works is, you want to create, so you have a set of numbers, okay? So it's like 12 numbers, and they have this magical property that there are exactly 3 ways in which you can partition them into sets that add up to a certain number. Okay? Now what you do is you construct evaluations of the players for the different items. So you have 12 items in this example. And you say, well, I'll force each player to have exactly 4 items in order to achieve the maximum share guarantee by adding some large amount to the value of each item. Then I'm going to take this set of 12 numbers and multiply it by something, by an intermediate number like 1,000. So that sort of forces you to use one of the special partitions that you defined in that magic matrix. And then you add another perturbation value that sort of says, okay, so far the values were the same for all of the players. Now I'm going to perturb things a bit. And the way things work out is the maximum share guarantee of each player is going to be exactly the same thing, because basically you set things almost in the same way except for this perturbation. But by setting things in this way, you forced a lot of things. So you forced giving exactly 4 items to each player. You forced using one of the 3 partitions that are sort of special from the magic matrix. But then, because of the perturbation matrix, when you use each one of these 3 partitions, it gives the maximum share guarantee to one player, but then because of the perturbations, it messes up one of the 2 other players. So, a full answer would be a bit more technical, but hopefully this gives some intuition. That's a great question. So we did look at the data. We are actually taking it one step further right now and doing a user study where we email people and ask them to compare different solutions, but we have looked at the data quite extensively. So the answer is on split data, you could always guarantee the maximum share, give everybody their maximum share guarantee. So we don't have one instance of the data where you can't. I think it's actually really fascinating. I mean, just speaking about the data, there are many fascinating things at play here. So you can, for the first time, look at, it's the first large set of fair division data, and there are many things that you can see. So for example, you can check things like when you impose fairness properties like maximum share guarantee, how much do you lose in terms of social objectives like social welfare? And for example, you could say something like, maybe it's possible to get envy freeness, but I could impose something like maximum share guarantee, which is a weaker fairness criterion, and get more value in terms of social welfare. So that's one kind of thing we're looking at. Another really interesting thing is for the purpose of studying envy, people have done experiments, but in these experiments, they basically say, here's a bunch of virtual items, and here is your value for each item. Now, how do you want to divide things? But then envy doesn't really have a real meaning, because what you really care about is the value that you get for your bundle and the value that other people get for their bundles. But that's what happens when the items don't have a real meaning for you. And what Split-it allows us to do for the first time when looking at the data and asking people about their actual instances is actually, asking them about envy freeness with respect to items that actually exist. So that's like just another example of the really cool things that you can do with this data.
If you generalize, say, look at the dynamic version of the problem, or even with uncertainty, where the valuations and preferences would change over time, and also the rearrangements would incur additional transaction costs. So is it still the same problem, or do you get into a new class of problem?
So are you thinking about a setting where the set of goods to be allocated changes all the time?
Not the set of goods, but the valuations, so the prices, but also the individual preferences of the agents.
Yes, that's a great question. So, so two quick answers to that. If the valuations change over time, so there are different ways to approach, thinking about dynamics in these fair division settings. Valuations changing over time, I guess you would be thinking about reallocating the items all the time.
But the change is not free, it costs.
Oh, so if you want to make a change, you have to pay a cost for changing. So as far as I know, it's not something that has been studied. The closest variant that I can think of is in cases where you allocate computational resources, which is something I have looked at and other people as well, so you think about settings where we have multiple resources like CPU and RAM and bandwidth, and people need them in certain proportions, for example. And then you have situations where people come and go and change their demands over time. So this is a very good example of this. The systems community, for example, a paper out of Berkeley by Godzi et al., have looked at this setting, but not from a formal viewpoint. So they just said, if you change your preferences, we just reallocate without imposing a cost on you. So I think there's a very nice question here of how to model this right. From a more formal perspective, the kind of things we have looked at, for example, is if people arrive over time, how can you, but don't change their preferences, how can we guarantee fairness to you, even though we would want to allocate more resources later to other people, and at the same time be efficient in some way? So that's a problem where there is some work. The variant you're talking about, I think it's definitely very practical. People have worked on it, but as far as I know, there's no theory about it, so it's a great opportunity. Thank you.
So one of the fabulous things about being at Harvard in the Boston area is that there are amazing and wonderful and brilliant people around, and one of the disadvantages